Hello and welcome. This is Rotational Motion, part 4. Now, in the last video, I talked about the rotational form of Newton's second law. Newton's second law, which says the net force acting on an object will be equal to its mass times the acceleration. Now, for a rotation, this will be replaced by the net torque on the left-hand side, one from 1 to n. This is the net force, net torque, equal to the object's moment of inertia, which is I, times its angular acceleration. Both angular acceleration and the moment of inertia are with respect to some axis. It could be any shape. This is the axis of rotation. Okay, so let's imagine we have an object like this, like a wheel, let's say. It's a cylindrical object and it's rolling downhill, and there's a cliff here. Maybe there's the bottom of the cliff or ocean or something. So right before it hits the edge, okay, it's supposed to move on a horizontal line. I'm talking about the center of mass now, which is for a symmetrical wheel, that would be the center, geometrical center. So this arrow here represents the center of mass velocity. Okay, so once it leaves the edge, it's going to follow a path, roughly a projectile path like this. Okay, so while falling like that, it's still also rotating, okay? So we have this motion, which is of two parts, rotation and translation, plus translation. By translation, I mean the motion of the center of mass. Now, imagine a line tangential to that parabolic path. This is center of mass velocity later. Right before it's going to hit the bottom, the center of mass will be pointing that way, etc. Okay, but it's also rotating about this axis that goes through the center of mass. There is this rotation. All right. So it's not a point particle anymore. It's a 3D rigid body. So we have to analyze both kind of motions, both rotation and translation. And how do we do that? Well, this is a sphere or a cylinder or a disc made of little tiny parts, right? Let each part be as small as you can imagine, okay? Maybe like a cube here. Now the total mass is m, and what we have here, little m, or let's call it mi. I is an index that tells you which little particle it is, okay? So there's another one here. This is the jth particle. Here you have, j plus 1, etc. You have 1,000 of those. They make up the whole object. Now, what about the velocity of that mi? All right. Now we're going to think this in terms of the idea of relative velocity. Okay. Now, what do I mean by that? This center of mass velocity is measured with respect to a frame here. I'm going to call it the ground frame, okay? An observer sitting on the ground, okay? The y and x axes, and there's z if you want. don't worry about it right now. Just x and y is enough. So when I say VCM, I'm talking about a velocity with respect to that ground. Okay, I'm going to put comma G. That means the center of mass, the velocity of center of mass with respect to the ground, or whatever your reference frame is. Okay, so that's going to be our notation here. Now, since we have an axis here and the rotation about that axis, that MI being r away from that center is actually going in circles around the center of mass, this blue circle, right? So on that circle, we have this tangential velocity vector. Tangential means it's going to be perpendicular to that radius here. So something like this. Okay. So it is a tangential velocity, Vt, of the ith particle that makes that disk. Okay. So following the same notation though, I'm going to call it Vi, comma, Cm, meaning the velocity of the ith particle on the object with respect to the center of mass of the object. All right, that's our reference frame. So we have this ground reference frame. We also have the reference frame, which actually moves along that parabolic path here. Okay, that is a center of mass frame. Okay. Now, VCM doesn't have to be a constant, of course. I mean, it changes here, obviously, the direction-wise and also magnitude-wise. Okay, but our analysis is generic, so it applies to frames which are not moving with constant velocity. Okay, it's general. So this is the center of mass frame. Okay, so I believe you are familiar with this idea of relative velocity. Okay, I mean, leave the rotation for a minute. Just think about a really simple case. It's like, let's say you have a platform here. Let me show it here right there. Okay, it's like a car of a train or something, but it's like really big. And on top of this, you have a car. Okay, you're towing a car. This could be a tow truck. Why not, right? So, and this platform is towed. So it does have some speed, okay? I'm gonna call this, let's call this object B. And this is object B, which is our car. So the platform here is moving to the right with some speed. I'm gonna call it VBG. Ground is our reference frame. But the object itself is also a reference frame. In that sense, the car may be also moving forward, okay? So I'm going to call it VA with respect to B. All right, maybe you didn't tie the car, it's just moving. But then what is the velocity of the car with respect to the ground? If you remember this, what we do is we add them, okay? This is the addition of velocities, also called the Galilean transform. VAB plus VBC, not C, G, ground, all right? So if you can line them up like this, you look at that index B, right? You have B here and B there. You're gonna get rid of those B and write this as VAG, the velocity of the car A with respect to the ground. Okay, I mean, that's very intuitive, right? I mean, if the platform is moving with 30 miles per hour, and then the car is moving with 5. Car's speed with respect to ground is 30 plus 5, 35. Addition of velocities. We're contracting this index here. Contraction. All right, so that's the idea. Now, it's a vector sum, so they don't even have to be in the same direction. It could be any direction. You're just adding vectors, right? 2 vectors added will give you a third vector. So in general, this could be as simple as this. So this is what VAB is, and then this is VBG. This will be VAG. Now let's apply it to the velocities here again. So remember, VI, CM meant the velocity of the ith particle in the center of mass frame with respect to the center of mass. And that is perpendicular to the radius, the tangential velocity. Like particle J here, that will be moving in that direction, etc. Okay? But now we're going to add that to VCM, G. That is the velocity of the center of mass in the ground reference frame. Okay? So that index here that will be contracted is VCM, and this will be equal to what? VIG. All right, so when you add those 2 vectors, you will get the actual velocity of that ith mass with respect to the ground. All right, so you can, I mean, I don't want to clutter this graph too much, but let me just do it anyway. So you carry this VCM parallel here, right there, like this. And then you add these 2, which will give you, let me use the rainbow pen, something like this. This will be the velocity vector right there for MI. Okay, so once we obtain that vector, VIG, what can we do with it? Well, moving objects have energy, right? Why don't we write the kinetic energy for that? Only for that particle. I'm going to call it Ki, which should be equal to 1/2 MI VI, G squared, right? I'm just using the symbol for magnitude, those 2 bars, the square, and then, all right, so I could write it as 1/2 MI VIG dot product by itself. That's what square of the magnitude means, okay? So I'm going to take this and then square it. Let's write it explicitly. So we have here 1/2 MI. Now, if I multiply this by itself, now I will have VI center of mass squared, okay, and then plus V center of mass with respect to the ground squared, plus 2 times VICM dot VCM G. Okay, I just expanded that square. All right, so that's what we have. That's only the kinetic energy of that ith particle. Now, here's what I want to do. I want to find the kinetic energies of each particles. Every particle that makes up this object. I'm going to write down the kinetic energy, which is this, and I'm going to add them up to find the total kinetic energy of this object when it's free falling, but also rotating, all right? So I'm gonna sum. The summation will be over index I. I goes from 1 to a large number, number n, ki. All right, so let's see what we have now. Now I have 1, 2, 3 terms. The first term will be 1/2 summation over I mi vi cm squared. All right. Okay, plus 1/2 I mi vcm comma g squared, plus there's 1/2 here, there's 2, so we get rid of those, and then summing over I mi vicm dot vcm comma g. Okay, so 3 terms. All right. Now, the second term, there's a summation over I, of course, but the only thing that you're summing over is masses. So it just gives you total mass. We already know what the second term will be equal to. This is nothing but the mass of the object. I'm just going to call it m here. All right. Now, let's think about the other two now. Okay, let's think about the other two. Let me just move this up a little bit. All right. So let's take a look at this third term here. All right. So we have the summation here. Mi vi with respect to the center of mass. Okay. So what is it? Now, let's recall the definition of center of mass. Recall. Okay, I can't spell. Okay, center of mass. Like the center of mass coordinates can be found by considering the sum. You multiply each mass by its position vector. You add them up and then divide by total mass. Therefore, starting from here, you can come up with, displacement in delta t time, and then take the ratio, find average velocities, and then take delta t to 0, consider the limit, or take the derivative in other words, and you come up with the center of mass velocity, right? Center of mass velocity will be 1 over m mi vi. Okay, so that's a general idea. In this case, though, VCM is what we call VCM comma G, right? So comma G 1 over m summation I from 1 to n mi, and then of course in the beginning we wrote VIG up here, right there, as VICM plus VCMG. So VICM plus VCMG. Okay, so what is happening here? We have from the first term, this is nothing but this guy here, that thing in green, right? Times, or divided by m, of course. We have I, mi, vi, cm divided by m plus, now 1 over m times I from 1 to n, mi, times VCM, comma g. But this is nothing but m, which cancels that. So on the right-hand side, I basically have VCMG. Okay, this, which I have on the left-hand side as well. So this can only happen if this term is 0. All right, so the sum over velocities in this fashion, by definition, has to be 0. Otherwise, it won't be the center of mass frame. All right, so this is 0. Okay, the third term is 0. So what does that mean? It means the kinetic energy can be written as, okay, let's start with the second term here, 1/2 mass times the center of mass squared plus, now we have this term here, the first term, 1/2 sigma I mi vi cm. All right, now this is the center of mass frame, and we're thinking about rotations around that frame, which are perpendicular to the radius. We saw that in the beginning. This means that every point on that object, the values of I go from 1 to n. Remember, for every value, we have a common angular velocity, omega. Remember, omega is the same for all points on the disk. What changes is VI's. So I'm going to write that VI in terms of the omega by multiplying omega by Ri. This is Ri here. That is the distance from the center of mass, or axis of rotation. So if I take this and plug it in here, take it and then plug it in here, I will have the square of omega and then square of R. So 1/2 summation from 1 to n, okay, mi Ri squared times omega squared. And you're already familiar with the second term. This is nothing but the rotational kinetic energy. Recognize this as the moment of inertia. Then we have 1/2 I omega squared, okay? So the total kinetic energy, or the kinetic energy of the object with respect to the ground frame, has two parts. It's the sum of the linear term. I'm going to call this kinetic energy linear. And then we have the rotational. Okay, rotational, which is 1/2 I omega squared. Just add these, and then you'll get the total kinetic energy. And that holds true for any shape, okay? It doesn't have to be a regular sphere or, rotating disk or anything. It applies to any object, okay? So, and as you see, this is just spinning in air, okay? Let's focus on something more specific, like how about what happened before the object reached the edge of the cliff. Now, while it was rolling on the cliff, okay? Let's say it's rolling without slipping. So let's see how this applies to that case, okay? So I'm gonna open a new whiteboard here. And so let's go back to the beginning. What happened before the object reached the cliff? So let's say here's our disk rotating wheel, all right? And it's moving to the right along the horizontal, let's say, surface. Now, this is rolling without slipping. Without slipping, which means the contact point here is not rubbing against the surface, okay? At that contact, you have a contact and the objects, not the object, that point has zero velocity. It's not moving with respect to that point, okay? That's stationary at that instant. That's not without slipping really means. Okay, so let's apply this analysis again. So we have the motion as rotation and also translation. The translation comes from the center of mass right here. If it's a uniform disk, the center of mass is also the geometrical center, of course, center of mass. So as the object rolls, this point moves also on the horizontal line. So that's where we have the center of mass velocity, VCM. Okay. And the radius is R. So a point on the rim, let's say, this is our ith particle, right? Now this point will have a velocity with respect to the ground. Let's keep those indices, okay? VCMG, this was, and then, excuse me, now we have this here, which is VI, we're talking about the ith particle here, right? With respect to center of mass. How do I know it's pointing to the right? Because it's the top point here and it's going to be perpendicular to the radius. That's why it's pointing to the right. Okay, but there's also the velocity of that point on the rim with respect to the ground. VIG, which I know how to write. That is VICM plus VCM with respect to the ground, right? And that's true for every point. But let's just focus on points on the rim for now. Okay, the points that will have contact. Like right now, there's this point which is touching the ground, but I know that a second later, this point over here will meet the point on the road like this. This point over here will come there. This point here will be there. Okay, so there's going to be that connection here. I know that these points will be over there. Like once it completes one cycle, which corresponds to, 2 pi radians in terms of rotation. If it's rolling without slipping, the center of mass will move a distance equal to 2 pi times r, right? If every point on the rim has a 1-to-1, relation or correspondence, whatever you call it, to the points on the ground, if it rotates one time, the center of mass has moved a distance 2 pi r. Okay, I think that makes sense, right? But let's go back to this calculation of velocity now. Now in this picture, if I add VCM to this, I will get, let me use what color? Let me use green. So this will be VIG. How do I know that? It's simply, parallel transporting VCM here, and then tail to tip, the usual addition of vectors. But what if I consider a point right here? Now the tangential velocity is this way. And now this is general, right? I mean, it doesn't matter if this VCM is increasing or decreasing. We're talking about instantaneous velocities here. So at this instant, maybe the ith particle or any particle on the rim will have a velocity that's pointing in this direction. Okay, that's here. But VCM is still to the right, of course. So here's VCM. And if I add those two, let me use green again, will give me a vector that points this way. Okay, so if you trace the points that I travels as the thing rotates, you'll get this interesting graph that goes like that. What about a point right here in the bottom? All right, let's apply the same logic here. Now I'm going to use black right here. This will be the tangential velocity, which we call VI, CM. All right. Now, what am I going to do? I'm going to add VCM to it. I'm going to use red again, VCM. I parallel transport VCM to here, and then apply the graphical method of adding velocities. You go this way and then come back, okay? You know how to add those, right? Tip to tail. But here, see, it's rolling without slipping, which means for this point, at that instant, VI, G has to be 0. Remember, there's no rubbing. It's just rolling like this. At that instant, there is no relative velocity with respect to ground. It is 0. So what does that mean? If this is 0, this means, okay, I'm going to use the same color here. So it's going to be really obvious, right? VICM plus VCM with respect to G is equal to 0, which means these two actually have the same magnitude but opposite directions, right? So VICM is equal to negative VCMG, only for the bottom part. For the contact point. Well, at all times, there will be a point which is in contact with the ground. Whichever point is, that's the point I'm talking about. They are in opposite directions, but their magnitudes are the same. VICM magnitude is equal to center of mass magnitude, center of mass velocity. Okay, so I'm going to take this and bring it all the way to here. So what happens? VIG at the top. If you think in terms of magnitude, it's equal to VIG plus VICM. They're in the same direction, but they have equal magnitude. So it is 2 times VCM. Okay, so we got this very interesting result now. I'm going to draw it here again. When you have an object like a disk or cylinder or a sphere, when it's rolling, if you consider I'm not going to use the notation center of mass anymore. I'm just going to call it V. If this point, which is R above the contact point, is moving to the right with speed V, right above it, we have this point here, which is 2R above the ground, and that is moving with speed equal to 2V. And then R below it, the contact point here, V is 0. All right. So it's interesting. Like if you actually roll an object and then make a movie, you know, film it, and then play back the movie, you know, especially if you do it really fast. I mean, if you roll it really fast, you'll see that the top will be blurry, okay? The camera will not really focus well on the top. But on the bottom, you will have a crisp picture. Try it, okay? And that's because that point is not actually moving at all. If it's not moving, okay, you get a good focused object. And if you move up, if you look a point above, like the center of mass, you know, it's okay, but it's not as focused as the contact point, but the fastest point is on the top. All right? So these are the velocities with respect to the ground level. Now, compare this to not an object which is rolling, but walking, okay? When you're walking, let's say, I'm gonna draw a stick figure here. This is the torso of the person, and now these are the legs, okay? A really bad picture, but you get the idea, okay? The person's walking. As the person's walking, okay, so one leg is here. The shoe is on the floor, and the other leg is moving forward. It's in motion, the other leg. Now, the one that is in motion is obviously, you know, is moving. It has a non-zero speed, but the one that is pressing on the floor is not moving, right? V is 0 here. Okay. Imagine you had many, many legs, you know, something like this. A cartoon character. 1, 2, 3, 6 legs rolling like this. Same idea. The leg that is touching the floor, or the feet or the foot that is touching the floor, is not really moving, but the rest are all moving, okay? And increase the number of feet to infinity, and you'll get up rotating, you know, a cylinder or something. Okay, so I hope this picture explains what's going on here, all right? So again, the center of mass in one rotation moves a distance equal to 2 pi r. 2 pi r. So that 2 pi r is the total distance. Now let's consider a constant, okay, velocity. Then I will have 2 pi r will be equal to v center of mass times the period of rotation, t, period. Okay, period. But I also know that the period, if I divide 2 pi by period, I get omega, angular velocity. Okay, so this way now I'm relating the angular velocity to the center of mass velocity, right? If I divide both sides of this equation by t, I will get 2 pi over t times r equals v center of mass. And the left-hand side is nothing but omega times r. A very important relation, right? For objects which are rolling without slipping. So, how does this help us in solving problems? Well, it's the kinetic energy. Let me open up a new whiteboard here. Remember, the kinetic energy had 2 parts, one from translation and one from from rotation. So kinetic energy of an object is equal to 1/2 mass of the object times center of mass velocity squared plus 1/2 the moment of inertia about the axis of rotation times omega squared. Okay, so let's apply it to a, let's say, solid sphere. Solid sphere, which is rolling without slipping. Now, a solid sphere has a moment of inertia equal to 2/5 m mass times r squared, where r is the radius of the sphere. Okay. Now let's write the center of mass velocity right here. Let's write the kinetic energy of this object. So we have 1/2 mvcm squared. Now in the second term, 1/2, this comes from the kinetic energy. Then I, which is 2/5 m what? R squared. Then omega squared. But remember from the previous slide, the center of mass is equal to omega times r. Therefore, omega is equal to v center of mass divided by r. So this times, so 1/2 times 2/5 mr squared times omega squared, which is v center of mass squared divided by r squared. Now what happens to the r squareds? They go away. All right, and we can simplify this. Okay, so we have 1/2, 1/2, 2/5. So 5/5, 5 plus 2, 7/10. M v center of mass squared. All right, a new expression for kinetic energy of a solid sphere, which is rolling without slipping, 7/10 m vcm squared. All right. If this was a cylinder, it would be a different story. Cylinder. A solid cylinder. A solid cylinder has a moment of inertia of 1/2 mr squared. Then the kinetic energy would be 1/2. The first term is the same, 1/2 m vcm squared. But now plug in the moment of inertia, which is 1/2 mr squared times vcm squared over r squared. All right, so 2, right? We have 3/2. 3/4, I mean, 3/4. m VCM squared. Okay, this is for a solid cylinder, which is rolling without slipping. Okay, so the shape of the object also determines what energy it'll have. So you could compare two objects of same mass. Let's say we have a solid sphere versus solid cylinder, and they weigh the same, and the radii are the same, okay? And then you roll them. Like you could do one of those tests like Galileo did. All right, so you could use an inclined plane. Like this. Okay, oops, didn't want to do that. Let's say this is height h. This is irrelevant, okay, it doesn't matter. But we have here a cylinder. And a solid sphere. Okay, and they have the same mass, m, m. And they have the same radius, r, r. And then you let them go. At the same time, they're going to roll down without slipping. Which one will reach the bottom first? All right, it's a race. Okay, who's going to win the race? How do you do that? So it's an energy problem, and let's ignore friction. Okay, now when I say ignore friction, I'm talking about the kinetic friction, okay, which is not present. We have rolling friction. Let's not go into that. Of course, if there's no friction, you will not have rolling to begin with, right? It's just going to slide like on ice. So we don't want that. We want to have a nice clean roll without any slipping, but we don't want to lose energy, lose mechanical energy in form of heat. That's what I'm trying to say when I say ignore friction. Okay, so use energy concepts and just conserve the mechanical energy for both objects. Okay, now remember, for a sphere, the kinetic energy is given by this 7/10. Why do I have 7/10 here? It comes from here, 2/5. Okay, so 2/5 here makes 2/10, 5/10, 5 plus 2, 7. Similarly, for the solid cylinder, I have 1/2, 1/4. So 2/4 plus 1/4, 3/4. Okay. So their initial energies are the same, which is just potential energy, m, g, h. That's for both objects. Initial velocity is 0, so it's only potential energy if you consider this level to be your reference. If y equals 0, y, x. But when the objects reach the bottom, the potential energy will be 0. Instead, we have now kinetic energies. So the cylinder will have this 3/4 m. I think it's a small m, right? 1/3 m v. I'm going to call it cylinder vc or cy, v cylinder squared. Now, when the sphere reaches the bottom, it's going to have the same energy, only written differently. It's going to be 7/10 mv, okay, sphere, sp squared. All right, now just compare these two now. Get rid of m's. All right, so you can divide this by 2. You will have 3 halves vcy squared is equal to 7/5 esp squared. So vcy over VSP squared is equal to 7/5 times 2/3, and that's 14 over 15, right? So this will tell you actually which one is faster when it reaches the bottom, right? With this speed ratio, you know which one's faster. All right, so okay, so let's just write this BCY is equal to square root of what is 14 over 15 V S P sphere. All right. So sphere has a greater velocity. Sphere will win the race. All right, let me stop here.